Okay. All right. Let's get started. It's been a while since we've met in person. It's been for you, other than the recorded lectures, been maybe a little bit of a maybe relaxing break. I know for me, it's been a pretty intense few days between on Friday when we had our green and white day recruiting event, and then on Saturday when we had, that was Friday and Saturday, and then starting Sunday. And actually, all the way up to this morning, we had our ABET assessment visit. So it's been a pretty intense few days for me. I felt like a human ping pong ball these past few days. But that's over. Everything's going well. So let's get back to the wonderful world of statics. Okay. Let's talk a little bit about some housekeeping items. So the homework, the outstanding homework is graded except for the last one. And full disclosure, that one's my fault because I had the solution done. I just, with everything being so busy, I just hadn't had a chance to give that solution to the TAs yet. So that's on me. But the solution is posted. It's on Blackboard, so you all have it for review purposes. I'm going to give the solution to them today so that they can begin the grading, but you all have the solution at your disposal. Before we begin, I'll go ahead and say right off the bat two things. One, just with the just stuff I've had to do for the past few days. If there's any outstanding emails that you've sent me that I haven't responded to, I am sorry. I will try and get to those as soon as possible. I have already had some requests to post some review problems for the exam. I haven't done that yet, but I've collected a couple. I just need to put them on Teams. I will do that, okay? In terms of the exam, I'll go through the logistics a little bit, but one thing I will tell you is that in the middle of all this, these crazy last couple days, not only did I make the exam, but I did have time to do the exam. So I always take the exam that I make to make sure that it's not too time intensive. I was able to do it in 15 minutes, so I don't think you should have too much problem getting it done in an hour. I always tend to employ a rule of 3. So however much time it takes me to do it, I multiply it by 3, and that's how much time it should take you to do it. And now that we've already been through an exam in here, the logistics aren't really any different, so it should be pretty straightforward. So we're going to do what we did last time with timing. It's going to open. Oh, I didn't change this because I had moved the day. So no, the exam isn't open. That's supposed to be Friday, 22nd. Sorry about that. So, whoops. Remember, I moved the exam from Wednesday to Friday, but I didn't change that on the slide. My apologies. Okay, so the exam is going to open up at 12:58. I always I want to open the exam up a couple minutes early because what I don't want to have happen. Police officer ordered what? Is somebody asking for money or something? Good gravy. Man, I'm a popular guy. All right. It's my car's extended warranty. It probably is something like that. Okay, so the exam opens at 12:58. It's going to close at 1:55. It's designed to be 50 minutes long. And just like with last time, everybody's going to be given a blank set of scratch sheet, or pages to use for scratch calculations that you turn in after the exam. One thing that I might mention is, and I don't know if everybody watched it, but on Teams, I recorded a video after the first exam where I said, okay, here's some advice for the second exam. And I would probably, if you haven't watched it, do so, because there are some little things that if you were to improve or do, your grades would probably shoot up. One of the big ones was show as much work as you can. I'm a partial credit guy, but it is very difficult for me to award partial credit when there's no answer on Blackboard, there's no answer on your scratch sheets, and there's no work at all. You know what I mean? So do something, do some work. Try, give every problem the old college try. Hold on. Oh, it's because I clicked away from the screen. That's why there we go. Okay. Approved materials. Look, this is the same as last time. So in terms of the operation on Blackboard, it will be a forced completion exam. So once the exam is opened, you have to do it in one sitting. It is timed with auto submit. And so it'll save and automatically submit. That is for your benefit, not as a hindrance, so that if you don't hit save, it'll save it for you. The questions appear all at once as opposed to one at a time, so that when it's all said and done, you can scroll through your answers and make sure everything on Blackboard is what you want it to be. In terms of the approved materials, pretty much anything that's been distributed to you in the course setting, open book, open notes, you can use any resource on Blackboard. You can use lecture notes. You can even use the recording. So I actually don't even have a problem if you want to take some earbuds, and if there's something I said in lecture 18 or something, I don't have a problem with that. Homework solutions, etc. The big thing is you're not permitted to give or receive aid from another individual, okay? And that includes Chegg and all that stuff. It also includes like stuff people have posted online, and I say that not as a means of like chomping at, like, don't cheat on my exam. More often than not, I mean, I'm not trying to really be super tricky. I mean, I'm going to challenge you, but I'm not trying to create an impossible exam. If you follow the work that we've done in here, you're going to be fine. If you're trying to seek out other stuff online in the middle of an exam, more often than not, you're wasting time. If you just attempt the problem, you probably do just fine. The format is the same. There's going to be 4 to 5 short answer conceptual questions and 2 to 3 computational problems, okay? So I want to be clear on that there's a section of problems that are computational and that are conceptual, and a section that are computational. So like on the last exam, that problem 5, where it just said like determine the length of this cable, that's all it was just the length of the cable. And I think a lot of people were taking it like, oh, this is a 3D statics problem, I need to go in to do all this. No, you know, read the problem and answer the problem is definitely a strategy that will do you well on the exam. Please do me a favor and type out an answer for every question, even the computational problems. It really does help me out with the grading. Let's get into the topics on the exam. So the topics on this exam are basically everything that we've covered in here since exam 1. So that's really 2 main topics, rigid body systems and rigid body equilibrium. In terms of what we're going to do on the exam, it's basically this right here. So so from the rigid body system stuff, you need to be able to compute cross products and dot products. You need to be able to compute moments. So that's really sort of the star of the show on this second exam is the moment. So on the computation of moments, you need to be able to compute moments about a point in either 2 dimensions or 3 dimensions. And there's sort of 2 ways of doing that. You can do the cross product, R cross F, or you can say that the moment is equal to the magnitude of the force times the moment arm, the distance, the shortest distance from the point to the line of action of the force in question. Also being able to compute moments about an arbitrary axis by dotting the moment with the unit vector along the axis in question. Be able to resolve force couples. So remember a force couple, what that is: 2 forces, equal magnitude, opposite direction, parallel lines of action separated by a moment arm, or separated by some distance, which is the moment arm. And be able to generate equivalent force systems in 2D and 3D. And that's taking a rigid body with a bunch of forces on it and distilling it into maybe a single force and a single moment, or a third system, you know, the force applied at a certain distance away to generate that same amount of moment. Finally, rigid body equilibrium, be able to compute support reactions in 2D and 3D to satisfy equations of static equilibrium. The rest of this slideshow is just sort of the greatest hits of formulas that we have utilized over the past few lectures since exam 1. So first off, the cross product of 2 vectors, and now there's 2 ways of doing it. For the most part in class, I've been focusing on cofactor expansion, but if you think this is easier, I know some of you in some of your previous math courses might have used this because, you know, you just take the 2 columns and all the products this way minus all the products that way. If that's how you want to do it, that's fine with me. I'm not a micromanager. I just want the answer to be right. I don't care how you do it. Cofactor expansion is kind of like what I use because I think it groups all the I, J, and K terms a little better, but that's just me. Dot product of 2 vectors, so if you got vector P and vector Q, the dot product's a scalar. You just take the X coefficients, the Y coefficients, the Z coefficients, multiply the pairs, and then add the results. That's all the dot product is. It's super simple. Also, also recognize that the cross product and the dot product will yield the angle between 2 vectors. Probably the dot product's a little easier because it's less computationally demanding to compute the dot product. You're just dealing with cosines instead of sines, so that's not a big deal either. The formal definition of a moment, generated by a force. So the moment about a point generated by some force is computed by the cross product of r cross f, r being the position vector that starts at the point about which moments are taken and ends at any point along the line of action of f, and f is the force vector. The magnitude of the moment is the force times the moment arm. So hopefully that's old hat by this point. If you're doing moments in 2 dimensions, you are doing the cross product. You're doing a cross product of r cross f, but when you resolve all this, moments, let's say, in the xy coordinate system only generate a vector along the z coordinate system, or z-axis. It follows the right-hand rule, and the result is just rxfy minus ryfx. It's basically just this for one of the terms. So wherever we're dealing with moments in 2 dimensions, we tend to usually only deal with the magnitude because we know that the axis about which the moment acts is in the third axis. So if it's the xy plane, we know the moment acts around the z-axis. For moments about an arbitrary axis, we just dot the cross product with the unit vector that's along the axis in question. And if you want, you could do a determinant and do it all at once. So that's fine too. Force couples, if 2 forces have the same magnitude, parallel lines of action, and point in opposite directions, and they're separated by a moment arm, that's a couple. The moment generated by the couple is either r cross f, where take your pick as to whichever one f is, and if, let's say, this is f, then r is a vector defined from this force to that one. So you're always picking a vector and summing moments from that to the other one. Equivalent systems of forces, so that's when the sum of forces in system 1 equals the sum of forces in system 2, and the sum of moments in system 1 equals the sum of moments in system 2. Finally, we have static equilibrium. These are the support conditions that we deal with in 2 dimensions and some support conditions we deal with in 3 dimensions. I will go ahead and tell you right off the bat, I am not going to get hyper inventive with the support conditions that I present to you because I don't think that really adds any complexity to a statics problem. It's still just sum of forces and sum of moments. So you're not going to, I was going to tell you, you're not going to see any boundary conditions beyond what we've already seen, which is, pin conditions, roller conditions, fixed supports, and then we've had problems where it's like determine the force in the cable. So that will possibly be there as well. And that's it. So I'm going to shut up for a second, turn the floor over to you. I think I've already got one question here, so floor is yours.
Will there be a 3D equilibrium problem with support conditions?
Will there be a 3D problem with support conditions? So let me answer it this way. If there is, it will probably be hyper simplistic such that the math is fast. Let me just stop right here. I'm not going to give you one of these super long 3D problems like you had on homework 4.3 that probably took you hours to do and say 15 minutes, good luck. I'm not going to do that to you. That doesn't mean you might not have a 3D problem on the exam, but if you have a 3D problem on the exam, it's going to be structured in such a way that it's as straightforward as possible. Does that answer your question? It's possible that we have 3D on the exam. I'm not going to say yes or no, but I'm not trying to make this exam a time crunch. I'm really not. So we might have 3D, but there aren't as many forces to deal with. Or we might have 3D, but all the vectors are easy to write. Or I might give you some of the vectors or something like that. Because I'm not trying to make this a time crunch exam. I'm really not. Again, like I said, I was able to do this in 15 minutes. So. And that wasn't rushing. That wasn't like using Excel. I was sitting there with a pencil and paper and a TI-36X. I wasn't using a Casio. Can you believe that?
So you picked a good company.
Oh, my. It's like you really want to get a heated discussion. It's like Casio versus TIs. Or like 0.5 versus 0.7, lead. Like, you want to talk about preferences. This is where it gets really heated. All right, back to statics. Come on, the floor is yours. Any questions you have, I will be more than happy to try and address them. We can talk about homeworks, concepts, whatever. Floor is yours. Yes?
This is more related to like just the format of the test, but you said open notes. Is that like notes we've taken, or does that also include the class notes of our teams?
You can use your notes. I don't have a problem with that. Yeah, I don't have, if you have notes that you've taken in your notebook and you want to take those with you, that's fine. The spirit of the rule is that you don't enlist aid from another individual, but you took your notes, right? That's fine, you know. So yeah, that's completely fine. I don't have a problem with that. That wasn't fine. Well, I hope they didn't break their calculator. Bring a calculator, I will say. Make sure you don't forget that. And like one thing I will say, like last time, I will have a couple hard copy exams with me in case, you know, Huntington gets hit with an EMP and, you know, your laptop fries or something. I don't know.
Oh, this is my first in-class exam, so we bring our computers and submit it on Blackboard.
Yes, yes. So the exam will be administered. So hold on. One thing I will say, so whenever we come in and do the exam, we're going to have everybody like split up a little bit so that each person has a couple tables for a number of reasons, one of which is that I'm hoping that calculators or laptops don't fall off the desks so much. But the idea is that I will give you scratch calculation, like just blank paper that you can turn in later, but you'll do you'll submit the problems on Blackboard. So it'll be like a timed quiz that shows up on Blackboard, and you just type out, it's like your conceptual questions, most people are just typing those out, and then for the computational problems, you're working it out, and if the answer is x equals 2, just put x equals 2 and move on. So. Are we feeling nervous about the exam? Are we feeling good, bad, like this is going to be the most horrible experience ever? It's a cakewalk. Yes?
I just wish other classes were like this, like where you actually like prepare for the test.
No. No. Do you like my reaction? My reaction, support reaction. Oh, that was good. Yes.
Can you give like a couple examples of conceptual questions for
No, but how about I just post the answer key? Because then it doesn't matter, right? What's that? So let me do this. I'll answer it this way. I'm going to come up with some practice problems. I will try and come up with some conceptual problems, but I got to be a little careful because let me say this. So, and I saw somebody else raise your hand. I think you might have raised your hand too. Okay. So what I don't want to do, I'm going to be frank, okay? What I don't want to do is come up with some problems that are so close to the exam that you're like, oh, well, that was the same problem. He just changed 2 to 3. You know what I mean? So I had to come up with the exam first and then come up with some practice problems. I want the practice problems to prepare you, you know what I mean? But I don't want to just give you the test. I was being frank, you know. But I will try and come up with some conceptual problems. I will.
Would you just be able to go over quickly like the concept behind like the moments about the arbitrary axis?
Okay, yes, I'll be happy to do that. I'm going to do that in a sec. Was there a quick question, Matt, or do you want me to do this first? Do this first? Okay, all right. So the idea behind, okay, so here's sort of the concept. I think the easiest way to explain the concept is to start with this, okay? So in this case, so when we first define the moment, just the moment in general, okay, what we're talking about is here's a point in space, and here's a force going wherever, right? It's going in this direction. So we got a point, we've got a force in space, and then we say, okay, the moment is defined as r cross f. This is f, and r is pointing from this point to anywhere along this line of action. And that is a very general definition of a moment. But what we as engineers like to do is we like to say, okay, can we take this general definition and maybe boil it down a little bit to something that's maybe a little bit more practical and a little bit more useful, so we go to this. Now, what we find in this definition right here, so this is just dealing with moments and forces in 2 dimensions. So instead of the point being here, okay, instead of the point being here and the force going out in some 3-dimensional space, what we're saying is like, here's the point, and the force is restricted to 2 dimensions. So the force can't go in and out of the screen, right? The force can only go maybe up and down, left and right, somewhere restricted to this screen. And so we say, let's see what happens when we evaluate the cross product, okay? So we say, all right, here's R, here's F, because the position vector and the force vector is restricted to 2 dimensions. And when we evaluate our cross product, R cross F, we end up finding that a bunch of stuff cancels out to 0, except for this, okay, except for the K term. So whenever we have a moment dealing with forces in 2 dimensions, the moment is always rotating about a single axis, about the z-axis. And that's a very special case of a moment about an axis. If you have moments in 2 dimensions, you have forces along the xy plane and positions along the xy plane. The moment generates about the z-axis, okay? What we're doing here is instead of, so this is maybe a little bit more of a specialized case with that. So here what we have is we have, instead of dealing with moments about a point, we're saying maybe moments about a line, or moments about a cable, or moments about a shaft. So let's say, oh, I need some props. Let's say this right here. Okay, so this is my axis, right? And we've got some force being applied out in space, okay? So what we're saying is this force, so here's the axis and here's the force. That force is going to want to twist that cable a little bit, right? So the idea, this is sort of the best way of thinking of it. R cross F is how much moment you get out of that force. The idea is, let's say you got this much moment out of that force. What percentage of that moment is just about the axis, right? That's kind of what a moment about an axis is. So if I have some force out in space and I'm applying, and I'm looking, let's say the moment about this point, it's twisting that point. But what percentage of that is going along this line? So it's sort of like figuring out how much twisting is going about that line. And there are some very significant examples of that in all branches of engineering. If we have an element that's being twisted, it responds differently than if it's being bent, right? So it's just isolating the amount of twisting about that axis in question. Does that conceptually kind of answer it? And I'll admit, of all the topics that we teach in this course in general, that's kind of like the most Star Trek-y one that we have. It kind of gets, it boils down a little bit more from there. So admittedly, that one's kind of tough. I'll completely agree with you. But does that answer that? Is everybody else okay with that definition? Okay, good. Oh, who's first? Oh, okay, all right. Yes, ma'am. 3.78. Which homework was that? 3.5. All right. Let me go through that, and then let's see. Tell you what. Oh, discard. Let me do this. I'm going to pull up the solution, and then if there's any one piece it's like, okay, I don't get that, we'll go through that, okay? You said 3.5? Okay. Okay. So this one right here. Okay. So let me zoom into this a little bit. Okay. So if I remember this problem, what we were trying to do in this problem was resolve a series of force couples, right? Okay. So what we were trying to do is we were trying to say, okay, I've got these force couples. I've got basically 3 of them in this problem. There was a 20 Newton force couple, a 25 Newton force couple, and I believe a 40 Newton force couple. Let me see if I can pull up a picture, because I think I'm just looking at some text and it's like it's not really helping us in terms of like actually trying to see what the heck's going on here. So, hold on. Technology, I know. So this is me pulling up the image PowerPoint so we can actually take a look at the problem. Okay. So this is the problem, right? Okay, all right. So the first thing I want to make sure that everybody understands is that conceptually, the sum of forces is 0. And that is always the case with systems that only have couples, right? Okay? The sum of forces, not the sum of moments, the sum of forces, okay? Whenever you're dealing with force couple systems, you are always dealing with scenarios where you have pairs of equal and opposite forces. Take the 20 newtons. Let's say this system only had the 20 newtons here, right? Okay, so 20 newtons. I've got 20 newtons going this way, 20 newtons going that way. If I sum those forces, what do I get? 0. There's nothing there, right? 20 newtons to the left and 20 newtons to the right, sum those up, the sum of forces is 0. But because they're not both going through the same point, because they are both separated by a moment arm, the sum of forces is 0, but the sum of moments is not, okay? So what we've got to do is see if we can resolve this by just looking at the moments. That's the nice thing about force couple systems is that when you look at it from an equivalent systems problem, so remember in equivalent systems how we had a body that had a bunch of crap on it, and we say let's resolve that into just a single force and a single moment. When you're dealing with a system that all it has is force couples, you can resolve it into a single moment because the sum of forces is 0. Does that concept make sense? Okay, so if that concept makes sense, then I think that we can probably reason through the rest. So let's take the force couple one at a time. So there's 2 couples. I thought there was 3, but there's 2. Okay, so here's the first force couple, okay? So it's 20 newtons, separated by a moment arm of 0.4 meters. So first off, you know, a moment is a vector. Vectors have magnitude and direction, okay? Vectors have magnitude and direction. So let's talk about magnitude. The magnitude is the one of these forces, the magnitude of one of these forces multiplied by the moment arm, which in this case is 0.4 meters, because if I got a parallel line, the shortest distance between those 2 lines is that right there, right? So the distance, the moment arm, is 0.4 meters. 20 newtons times 0.4 is 8, right? So the magnitude of the moment generated by this force couple is 8, okay? Now, what I did with this problem is I looked at it from an observational standpoint, okay? Remember, with force couples, there's sort of 2 ways of going about it. We can say, all right, the first way I can do it is I can actually try and write an R vector, write an F vector, R cross F, and get an answer, or I can look at it. And to be clear, the problem doesn't care which way that you write the vector. If I did R cross F or if I looked at it, as long as I'm doing it correctly, you will get the same answer. So if you're feeling like, oh, I've got to be able to look at it, no, that isn't going to be, I think, an issue on the exam. I think that there's enough buffer time there that if you actually want to write the R vector and do R cross F, that you can do that. But the way that I'm assessing it with this problem is, let me go back to the picture. Oh, nope. Is the right-hand rule states, and I admit, and I understand this might be a little difficult to see, the right-hand rule states that, first off, okay, does everybody see, and specifically you suggest the question, do you see that based on the diagram that this will cause rotation about the y-axis? Does that make sense? That these 2 forces, just imagine. So imagine you're standing next to this box, right? So the y-axis is up and down, right? Right, make sense? So imagine the box, right? Imagine this is the box, okay? So the y-axis is going up and down, right? And if you're right here, if you're yanking with 20 newtons and I'm pushing with 20 newtons, we're doing like this to the table, right? The table is doing this, and it's rotating about this axis. Here's the axis, and the table's rotating like that. Does that make sense? Everybody okay with that? So what I'm getting at is that the moment generated by this couple is going to be of magnitude 8, and it's going to be about the y-axis. So it's either going to be 8j or negative 8j. The big question is whether or not it's positive or negative, okay? And remember, the right-hand rule states that if my thumb is pointing along the axis, right, my thumb's pointing along the axis, the right-hand rule states that it has to rotate this way for it to be positive. But if he's here pulling like this, and I'm pushing like this, right-hand rule says it's got to rotate this way, but we're rotating it the other way, right? So that's why this first moment is negative 8j, okay? Does that make sense? Okay, if that makes sense, then the second moment, now the first one was observation. The second one, no, I'm not going to do that. I'm just going to do the math. I'm just going to do the math, okay? So because I've got forces about an angle, I've got trig, no, don't try and do an observation. Just let the math work itself out, okay? So whenever we're letting the math work itself out, what we need to do is pick one that we're going to sum moments about. So there is no, like, right one. I just flipped the coin. So what I did is I said, okay, I'm going to sum moments about this point right here. I might have done it opposite in the problem. It doesn't really matter. Let's just say this is the one I summed moments about. So in this case, R, it's this shaded thing, okay. R is going to be this vector. This is R, and this is F, okay? Does that make sense? Because I'm summing moments about point B. If I'm summing moments about point B, this one does not generate any moment. The only one that generates moment is this one, separated by this moment arm. So all you need to do is write a definition for R and F and just do R cross F. So R in this case is what? If I start at B and I go to C, I think I go, negative 0.75 K, is that right? Nothing else, right? So there's R, and F, now F, here's what's going on with F, okay? Now with F, all right, so if I look at these two forces are both along the XY plane, right? There's no dimension defining them in and out of, along the Z-axis, right? So it's going to be, you know, apolojunct times I plus apolojunct times J, okay? Now, we do know the magnitude of the force. It's 25 newtons. So all we need to have is 25 times a trig function in here and 25 times a trig function in here. The only thing we got to get right is the signs, the positives or negatives. So if I look at this force up here, this one right here, it is pointing left along the x-axis. So I'm going to say that this is negative along the x, and I'm going to say positive along the y because it's pointing upwards. So all you have to do is you have to say 25 cosine 40, because the angle is measured with respect to the horizontal, 25 sine 40. So here's F, here's R. So if I have R and I have F, I do R cross F, and that'll give me the second moment vector. So if you go back to the solution, here's moment 1, here's moment 2. Just add the two vectors together, and then you can do magnitude and direction. And magnitude and direction, so when I add the two vectors up, I got apolojunct times I, apolojunct times J. So the magnitude of the moment is just Pythagorean theorem, because at this point, it's just a vector like any other. So if I give you a vector that's apolojunct times I plus apolojunct times J plus apolojunct times K, how do you determine magnitude and direction? Well, magnitude, you just use Pythagorean theorem. And in order to determine direction, all you got to do is say, all right, here's the vector, divide it by its own magnitude to get a unit vector, and then what do I do? Inverse cosine of each of these, and boom, I've got the direction. And that's all there is to it. So I guess the follow-up question, and this isn't just to you but to everybody in the class, is that if I give you a vector, can you determine the magnitude and direction of that vector? Just period, you know. If you can do that, then all it is just writing moment vectors, summing them, and doing that. So, did that answer your question? Is there any specific part I didn't cover, or anybody else? That's a great question, though. Thank you. Any other questions? It ain't going to be that bad, I promise. It'll be okay. Especially since you have a professor who's preparing you for it. I'm just messing with you. I will honestly say I don't think that the exam has too many curveballs. I'm not saying there aren't some, questions. I mean, it's not going to be just, homework 3.78 instead of 20 newtons is 25 newtons, do it again. It's not going to be that, but I don't think that the exam is ridiculously challenging. I really don't. And if there's ever any, like, one of the other things that I want to hopefully convince you of, and maybe I will, maybe I won't, but what I'm not interested in doing, and I think I did a pretty good job with that, with the formation of this exam, is let's take some of the later problems that we did, those super long 3D problems. Some of the work was just in defining the vectors. You know what I mean? And what I'm not trying to do on the exam is trying to come up with situations where you have to just do all of that. You know what I mean? I don't want you to have to just spend all this time defining vectors and write, oh, here's the lambda, here's the r vector. There are problems where I'm making you do that, but I'm really trying to make sure that I'm not testing you on stuff like that over and over and over and over again. I'm trying to reduce the repetitiveness of stuff like that because it's a timed exam, okay? So it's something I really try and effort when I build an exam, is that if I test you on something, I don't want you to have to do the same thing over and over and over again. I don't think that there's any value to you as the student or to me as the professor having to grade it. So, well, I'm being honest. Yeah. Any other questions? Going once? Going twice? Want to be let out 12 minutes early? Tell you what, I will post problems on Teams. If you have any questions, you can come see me. But I'll stick around if you have any other questions for a little bit. But nothing else, take it a few days early.
I got in here at 101.
Okay, hold on for 1 sec.